I'm going to talk about everlasting multi-party computation. So let me first tell you and motivate to you what everlasting means in this setting, everlasting security. So the problem is that even if we trust our encryption schemes to be pretty secure now, at least some of them, future technology may break today's ciphers. And it's pretty difficult to judge how long something we encrypt now will stay secure. Can we trust the keys to hold for 1 year, for the next 10 years, for the next 100 years, or pretty satisfactorily for the next 10 to 20 years? We don't really know, because we don't know how technology will advance in that direction and so on. The only thing we can roughly estimate is Moore's law. And if you look at official key length recommendations, you will usually only see recommendations for a few years. No one will tell you what key you should use if you have really confidential data that should not be, that should stay secret for the next, say, 50 years. And because of this observation, I would advocate to use everlasting security. So everlasting security means that we don't even try to make any long-term assumptions about our crypto. The only thing we assume is that whatever we use now is hard now. For example, if I encrypt a message, send it over the network, I will not even try to assume that the adversary can't decrypt it in a year. All I want to assume is that the adversary cannot decrypt it right now. So what would this mean? Well, look at the typical protocol where Alice and Bob are exchanging data. Some of the data may be an encryption or somehow differently dependent data, dependent on some confidential information, and other messages may depend on some temporary secrets that are perhaps only needed to make sure that Alice and Bob perform the right steps in the code, in the protocol. And everlasting security essentially requires us not to send anything like this. Never send anything from which an unlimited adversary can decrypt the secret. Or slightly more formally, everlasting security considered adversaries that are computationally limited right now, but unlimited after the protocol ends. Because this guarantees that even if the adversary writes down everything he sees going over the network, he cannot later, when he can break, say, whatever, AES, read our data because the protocol was made under the assumption that the adversary can break this. So the protocol was proven secure, assuming that the adversary is unlimited after the protocol. Let me give you some well-known examples that actually have everlasting security. So from traditional crypto, we have statistically hiding commitments. These are actually everlastingly secure because although they are not information theoretically secure, you cannot break them after the protocol end, because breaking the binding property doesn't help you if no one is listening anymore, and the hiding property is unconditional. And similarly for statistically, you see. But I should say there are some caveats. There are some pretty tricky composition issues on these, so it's not as easy as it sounds. Quantum key distribution with computational authentication is another example. There you get a key that is unconditionally secure, assuming no one was able to break the authentication that is used to secure your public channel during the QKD protocol. Or the bounded storage that we heard in the first talk of this session is another example. Here, if the adversary after the protocol end suddenly gets unlimited storage, that doesn't help him. However, the problem with the bounded storage model is if quantum storage should at some point get cheap, well, this would not break our old data, but we can throw away the protocol. So we need some other protocols that are not based on quantum storage for the case that quantum storage becomes cheap at some point. So this talk will be about everlasting multi-party computation. So meaning I want to compute an arbitrary classical function, although I think quantum would also work, an arbitrary classical function in an everlastingly secure way. where everlasting, I refer not to the bounded quantum limitation, to the storage limitation, but to the computational power. So we can ask ourselves first, if we ignore the quantum possibilities, can this be done classically? Let's look. So assume we have an everlasting MPC protocol. Then it's easy to see that this actually implies a semi-honestly secure unconditional MPC protocol. Why? Because an adversary that breaks this, it is an unlimited adversary that, however, during the protocol doesn't do anything except following the protocol. So especially during the protocol, he's computation limited, because running the honest protocol should be possible in polynomial time. So this adversary also breaks this. Therefore, everlasting security is at least as strong as semi-honest unconditional security. And we know that this can't be realized without any, in the plain model, without using any additional trusted parties or anything like that. In fact, you can easily generalize the known impossibility to the case where you have some trusted setup, like a common reference string, a coin toss for free, commitments, public key infrastructure, signature cards. I will tell you in a moment what signature cards are. And actually, handling all of these is very easy. All you do is you show that you can realize all these in a way that is secure against semi-honest adversaries. For example, a commitment. How do I make a semi-honest secure commitment protocol? If I want to commit, I just tell you I'm committed, and later I tell you what I was committed to. If I don't cheat, this is a secure commitment protocol. So these are trivial to realize, and therefore they can't give us anything. Okay. But since it's the quantum session, let's ask the question, can we use quantum communication to solve this problem? So let's think about quantum everlasting MPC. And first, let's have a look at what we know what is impossible in the quantum case concerning MPC. So what we actually know by slightly general, reformulating old impossibility results by Myers and Lowe is you cannot do semi-honest multi-party computation in the classic quantum setting if the parties are unitaries. So for those who are not into quantum stuff, think of this just as non-erasing parties. It's a similar thing, whether they do unitary operations or non-erasing. It has, in this context, similar effects. So you cannot actually do a semi-honest multi-party computation protocol when you require the parties to be unitaries. And unfortunately, we can now apply the same reasoning as before. We can say, well, if we have an everlastingly secure protocol, the definition of security does not really care whether we have built our parties in a unitary way or in one that does measurements. It's the same as when you talk about erasures. It doesn't matter whether internally you erase or you just ignore data. So everlasting quantum security means also everlasting quantum security using unitary parties. And then with the same argument as before, it would imply this security. And that's impossible. And again, we can also check which additional setups would be trivial to realize semi-honestly with unitary parties. And you can go through them and see that CIS can be realized, coin toss can be realized, public key infrastructure can be realized, even shared entanglement that is given in a trusted way can be realized. They all can be realized semi-honestly unitarily, and therefore they cannot be sufficient for this, and therefore not for this. So we have excluded, unfortunately, already a lot of typical setups that could be used that we might have hoped to use. But if you compare the list here and the list on the previous slides, where it told us what is used less classically, you see that two are now gone, namely commitment and signature cards. So about commitments, well, we know that we can, if we are given a commitment, we can do quantum multi-party computation even in an unconditional way. So this has been known quite a while. So it was first observed by Bennett, Brassard, Crépeau, I think, right? And okay, Skubichevska, in 91. And actually, we got UC security of it in 2010, so we can even compose nicely and everything works. The problem is commitment is not something as a good setup assumption. Yeah, if I can't kind of say, well, a CIS, you just need someone who broadcasts it. It's much easier. But saying like someone gives us a commitment, it's not really clear what this would mean. So we don't want to assume that we have a trusted commitment that is kind of shared between the parties. However, signature cards is a different thing. So signature cards, I will tell in a moment how they are modeled, is something that we may even buy in a shop. So we might hope that perhaps those give us more. And indeed, we know from the prior work that if you have a signature card, you can actually implement an everlasting commitment protocol. So let me go into slightly more detail on that. First, what is a signature card? In our modeling, a signature card is something that is issued by a trusted authority, for example, the state or a CA or something, and it has three important features. First, it signs arbitrary messages for the owner of the card. Second, everyone knows the public key of that signature card. And third, and this is a crucial point, even the owner of the card does not have access to the secret key. And then we have Müller-Quade-Unruh 2010 that shows us we can do everlasting UC commitments from it. And from last year, from commitments, you get in a UC way unconditional MPC, and therefore if the commitments are just everlasting, you get everlasting, because you don't lose any security here. Seems good. Seems we have solved the question. However, this protocol was proven only against classical adversaries. So we can't use it, at least not if we don't go through the proof and see that it still works. So I skipped that. That's the definition of the UC model, but I don't have time for that. So let's assume we have a nice security definition for the quantum everlasting UC. So let me recapitulate the classical protocol that would give us an everlasting commitment that is even UC secure, and therefore we can compose it with other protocols and get the full MPC. So the first step would be to, if we commit to a message M, we commit on the message M using a statistically hiding commitment. That's fine so far because it doesn't leak the commitment. However, if you want to be UC and be able to compose with other protocols, as you need to get the big MPC thing, you need, for technical reasons, that the simulator can extract, so someone who can, for example, cheat about this signature card, can extract the message M without anyone noticing. So we need to add into the protocol this trapdoor. And for this, the idea was we want to force Alice to, when she commits to M, to always sign an opening information on M. And then she has to prove that she knows the signature on a valid opening information for this commitment. What effect does it have? Well, the simulator, those who know UC will know that, those who don't who have to believe it, sees all the signature queries. And therefore, since Alice proved that she knows the signature and the only way is to send it to this signature card, it means that the simulator sees also an opening to this commitment, because one of the queries is an opening. Oops, sorry. Therefore, he knows M, therefore we have extractability. There's another condition called equivocability, it's done similarly, I skipped that here. But the tricky thing now turns out to be this implication. Seeing all signature queries means seeing the opening. Why? So the crucial fact that we have to use here is that if you have a malicious prover who has access to a signer that signs everything except an opening, then it is not possible to send a proof that the prover knows a signature on an opening. Yeah? Alice can't prove that she knows something she can't sign. Seems intuitive, and the classical proof is the following. You take the extractor for this proof of knowledge, run it with Alice and the signer as an oracle, and by definition of proofs of knowledge, this extractor will output a signature of an opening, because this is what Alice proves to know. Therefore, the extractor finds a signature of an opening, querying only this oracle on known openings. That's a contradiction to unforgeability. But in the quantum case, it gets subtle. In the quantum case, the definition of a proof of knowledge not only applies the prover oracle, but also the inverse operation of the prover oracle. So that if you have it as a unitary transformation, it applies the inverse of that transformation. So now you have an extractor that queries this and this. Therefore, we have an extractor that finds a signature on an opening, given only using an oracle that only produces signatures of non-openings, and using the inverse of that oracle. Well, unforgeability does not guarantee anything about this weird application. So we don't have a contradiction anymore. And proving something like this is, as far as I know, an open problem. So getting a signature scheme that is secure when used like this, we don't know how to do it. Perhaps that's something that your techniques could be adapted to, I don't know, but at least what you said in the talk does not immediately apply. But it would be interesting future work. So what can we do about that? Since I have a bit more than 1 minute left, I can't go through all the details of the protocol, and therefore I have a simplified version here, which I also can't go through in all detail. But the basic idea is we have to make sure that we don't have the rewinding and the argument that we have unforgeability in the same proof step. And our solution is the following. Well, first, Alice still commits to the message M as before, but now she doesn't prove that she knows an opening. Instead, she uses a so-called dual mode commitment on the opening and proves that this commitment has the opening inside. Furthermore, a dual mode commitment is one that is hiding only for an honest CIS, but the simulator in some earlier Cointers phase can cheat so that the CIS becomes so that the simulator can just read out this commitment. And since Alice proves that this commitment, which the simulator can read out, contains the right information, we have a simulator that gets the opening. And if you go through the proof in detail, you will see we never used rewinding and the signing oracle at the same place. So now we can plug everything together. We get everlasting UC commitments from signature card, quantum secure, and plug this together with existing result and have everlasting security. And that's it. Thank you.
Any questions? Okay, I have one. So it seems important for your proof technique here that the adversary cannot pull the secret key out of his own signature card.
Yes.
So what kind of access does he have to the signature? Can he have quantum access to the signature card, a la what the Marx model is specifying, or is it classicizing the queries?
It has to be classical because, well, the thing is that we use the fact that the simulator sees the list of queries, and it's not clear how to define that quantumly. So it's not that I have an attack, but I'm not even sure how I would define the fact that the simulator has access to the queries.
Okay. So that means if you lift the model and assume that the adversary have quantum access to the signature card, we have an open problem there to work on. Okay.